Well, today we are going to start on a new topic, that is on the peritectic phase diagrams. And as you know, peritectic alloys are equally important like eutectic alloys. And let me give you a few examples. The copper and zinc, the classical brass, is a peritectic alloy systems. There are about more than 5 peritectic reactions present in the copper and zinc system. Similarly, bronze, copper and tin, an alloy has peritectic reactions. Similarly, many industrially important alloy, let us think of iron carbon, classical steel has a peritectic reaction, and peritectic reactions for the steel lies very low carbon concentrations, that's about 0.13% of carbon. So that means that peritectic reaction is very general in the phase diagrams, and many ceramic system also has peritectic reactions, like all the superconducting material, many of these has a peritectic reaction present. That is why it is very important, so that we understand the peritectic phase diagram and the solidification. In the first lecture, I will just try to explain the phase diagram and show you how the things happens. So classical peritectic reaction is given by liquid reacting with a solid phase, giving rise to another solid phase. This is the peritectic reaction. This is a very important reaction because most of the things alloy development depends on this reaction. So please try to understand that here one liquid phase reacts with another solid phase, one solid phase leads to formation of another solid phase. Sometimes it is written like this: during cooling it will form beta, during heating beta will dissociate into solid and liquid. So this kind of reaction can be represented in a phase diagram in this way. Again I draw the composition axis first, pure A, pure B ends, temperature, okay. So this diagram is completely different from eutectic. In eutectic phase diagram I have seen there is a dip at the center. Here it is not present. So this is pure liquid, this is the melting temperature pure A, melting temperature pure B, alpha, okay. This is alpha plus liquid, this is beta, the alpha plus beta, and liquid plus beta. So you can clearly see again there are 3 two-phase field, liquid plus alpha, liquid plus beta, alpha plus beta, and 3 solid phase field, liquid, alpha, beta, same like eutectic systems, but the diagram is completely different. In fact, this is not easy to draw. Sometimes students face difficulty in drawing the phase diagram. So for generalization I am just drawing the phase diagram of eutectic here, so that you can keep it in you can keep it here. This part remains same, this part varies, and there is a dip in the center. This is between C and D. So you can clearly see the difference. It is not at all looking very similar, rather it is different, distinctly looking different. So these kind of phase diagrams actually observe for systems when you have a large difference in melting temperature between A and B. As you can see here, TA is here, TB is there. Melting temperatures of A and B are large different. So whenever you have such a kind of large difference of melting temperatures and interaction between A and B, which will discuss later, is strongly negative, then you have this kind of phase diagram formations. So let me just discuss about these phase diagrams little detailed manner. Here the peritectic reaction happens at a temperature known as TP, this temperature, and reaction is taking place here, in which alpha plus liquid reacting with each other and forming beta. This is where. So, if you cool down this one, the way I have drawn the arrow, alpha plus liquid or liquid plus alpha, whichever way you say, reacts with each other and forms beta. This is where the reaction takes place. So, this is a horizontal line. So, I told you as a thought that any horizontal line in a phase diagram will give you the idea of phase of the reaction or some kind of reaction. So, at this temperature Tp, at the composition given by this, which I can draw, this is Xp, Xbp, the reaction happens. So, that means at this temperature Tp and composition Xp, L alpha, liquid and beta, 3 phases are at equilibrium. So, therefore, degrees of freedom here is 0. Why degrees of freedom are 0? Because we know degrees of freedom is given by C minus P plus 1, and here there is 2 components. So, 2 C is 2, P plus 1, so 3 minus P. So, if there are 3 phases present here, so 3 minus 3, P is 3, F becomes 0. So, degrees of freedom is 0 at this point. Now, similarly, in the 2 phase field regions where you have 2 phases alpha plus beta, alpha plus liquid, beta plus liquid, degrees of freedom is equal to 1, and in the single phase field like beta, liquid or alpha, degrees of freedom is equal to 2. Okay, you should remember that. Same thing here also, degrees of freedom at this point is 0, and here, there, degrees of freedom is equal to 1. On the other hand, in the alpha and beta and liquid regions, degrees of freedom is equal to 2. So, there is some similarity between this and this, but the inside diagram is completely different from the eutectic one. So, now upon knowing this, Peritectic reaction is distinctly different from eutectic. In eutectic reaction, 2 solid phases comes out from the liquid. Here, one solid reacts with the liquid, forms another solid. So, therefore, this reaction is completely different. Now, I will tell you why this reaction is completely different. Okay, so let me just reiterate again. You have a peritectic reaction isotherm at temperature Tp, composition Xpb, in which liquid reacts with alpha giving rise to beta. Now, how does the reaction happens? Suppose I have an alloy which is solidifying this composition Xpb from liquid state. So, I am drawing this vertical line and I am following it up. So, obviously, if I cool it down from liquid, this is my liquidus TL. Above liquidus, everything will be liquid. Only below the liquidus, alpha will start forming, and alpha will start forming and alpha will grow like a dendrite in the liquid. This is alpha in contact with the liquid. In this temperature between TL and TP, alpha will grow in the liquid like a dendrite. Okay, that is because this is the most easily formable shape possible in the liquid state. Now, when the temperature of this system will go down below the Tp, alpha and liquid will react, and if they react, they will form beta. How the beta will form? Beta will form at the interface between alpha and liquid like a layer, So, this is the beta layer which will form in between alpha and liquid. You can clearly see I am marking like a white chalk, using white chalk. This white layer is beta, which has formed because of reaction between alpha and the liquid. So, this is beta. Okay, so this beta which is formed on the alpha will immediately stop the reaction. Why? Because as soon as the thin layer of beta forms on the alpha, the contact between alpha and liquid is gone. There is no contact, direct contact between alpha and liquid. So, any further increase of thickness of beta is not because of the Peritectic reaction, but by Peritectic transformation. What is that? Well, let us little bit dwell on this matter. So, as you see here, as I have formed a thin layer on the top of alpha, thin layer, so between liquid and alpha. So, any kind of contact, direct contact between alpha and liquid is not there. Such a situation, for the reaction to proceed or reaction to go further, atoms in the alpha has to diffuse through this, layer of beta and come in contact with the liquid, because reaction is only possible when there is a contact, otherwise reaction is not possible. And here it is a liquid and solid, so therefore direct contact is required. When there is no direct contact, only way it is possible is that atoms in the solid alpha will diffuse through the layer of beta, come in contact with the liquid, and when it comes in contact with the liquid, it forms another layer of beta. Okay, suppose this is the layer of beta forms. So as it forms another layer of beta, the thickness of the beta will increase. So if for any further reactions, atoms in the alpha again has to diffuse through this whole layer, come in contact with the liquid, and the diffusion distance each time is increasing. Why? Because thickness of the beta layer is increasing. As the diffusion distance increases, the time required is also increase, because diffusion, you know that distance is equal to root dt, where x is the distance, it is the time, and d is the diffusivity. So as you increase x, d is remaining constant, same, time t increases. So therefore as the time increases, you need more time for the atoms to diffuse from alpha to come in contact with liquid, and after some time this time will be very large, so therefore no further diffusion is possible, and under such a situation you will always have some leftover alpha in the microstructure, which you cannot help. There will be always some leftover alpha present in the microstructure because incomplete reaction. This is the problem with all Peritectic reaction. Peritectic reaction under normal cooling conditions will never get completed. Will never get completed, and that creates lot of problem in the industry. Okay, which we will discuss, one or two case studies we will discuss in the whole class, in one of the classes, where I will show you that retaining this phase alpha, which is this phase, at a temperature lower than the table temperature, can create a lot of problems in the properties of the material. So as you see here, alpha is known as pro-peritectic phase, just like eutectic, I have discussed pro-peritectic phase because it forms before the Peritectic reaction, and beta is known as the peritectic phase, and because it forms after the Peritectic reaction. So you will have always pro-peritectic phase alpha retained in the microstructure because of incomplete reactions of peritectic reactions of this kind. So because of this, it can create all kinds of problems, as I told you. Suppose let me just explain to you the peritectic reaction which is present in the iron carbon phase diagram. Peritectic reaction present in the iron carbon phase diagram can be written like this: liquid reacting with delta iron or delta rather, okay, reacting with liquid and produce gamma. As you know that iron has three phases, alpha, beta and delta in the normal pressure, and delta is a BCC phase, BCC iron, and gamma is a FCC iron. Alpha is also BCC phase. So now in this reaction, liquid plus delta going to gamma, same thing will happen, and I will draw it again here. So I have a delta dendrite coming in the contact with the liquid, and as the reaction happens, this reaction happens at 1394 degrees Celsius temperature. As the reaction happens, you can see here that gamma will form like a layer around delta. This is gamma, it is better to mark like a chalk, gamma, and as time goes, gamma layer will increase one by one, but it cannot consume the full delta. It cannot consume the full delta. Delta will remain rather in the microstructure. And so okay, so another, as you give more time, another layer of gamma will form, but you know delta will retain because of incomplete nature of the reaction. Now suppose this whole microstructure is solidified and you are retaining it at room temperature. At room temperature delta is not stable, but gamma is stable. Gamma will remain there. Delta or gamma is also not stable anyway, but gamma will undergo the other reaction to form perlite anyway, but delta is not stable at room temperature. Delta will form alpha iron at room temperature, or it may not form because of pressure effect. whatever it is, this will create a lot of problem in the final properties of the material, because ultimately finally in the steel what you want is alpha as a primary phase and perlite. You do not want anything else, okay, for the normal steels. So you can see here this happens only with very low carbon concentration in the steel, and because of very low carbon concentration in steel, these category of steels are basically stainless steel, and therefore this is a very critical problem in the stainless steel. In all stainless steel you can have this problem, and in fact there are other stainless steel contain iron, chromium and nickel other than carbon. So therefore there actually chromium can segregate and reacts with carbides and form chromium carbides. There is another additional problem which we will discuss later, but from the perspective of the Peritectic reaction you understand that this can create problem. Another example I will give it to you which is very interesting. All the headphones nowadays used for iPad or mobile phones has this very small magnet into the headphone, and these magnets are actually very strong, and most of these magnets come from China, and China has the largest source of this material. That is why they have the monopoly. Almost 96% market share is by China. So these magnets actually are this type. It contains neodymium, iron and boron, okay, and iron and boron most of the countries has. What we do not have is the neodymium. Neodymium is a rare earth metal. So these alloys actually undergo Peritectic reaction. Liquid with gamma iron reacts and form a NdFeB phase. This alloy forms. Remember, this is the magnetic phase. All the speakers actually hard magnets which we use to listen music or listen all kinds of other things. So like we can use for other purpose also. This is the magnetic phase. This is the hard magnetic phase. So if you want to use increase this strength of that, you want to have more of this phase. But as you see here, because of this Peritectic reaction, you will have formed gamma phase present, gamma iron, liquid, and this phase will form on the layer between gamma and liquid like this. But as an engineer, what do you want? You want this because the hard magnetic property is provided by this. This is what is this NdFeB phase, okay, Nd12FeB actually. So because of that you want to have maximization of this particular phase in the microstructure, because this will give you more energy product or more stronger magnets, hard magnets. But it will never happen, because by Peritectic reaction there will be some gamma left over, and this gamma will create problem, because if this gamma actually later on room temperature will transform to alpha iron, and alpha iron is a soft magnet. So if you have a soft magnet inside this at center of the hard magnet, this will reduce the strength of the hard magnet. So therefore there must be some solution to that. So what I am telling you is that Peritectic reaction creates problem in the industry actually. All this Peritectic reaction like stainless steel I told you, or in the magnets, it creates problem, and the main problem originally from is nature of the reaction. The reaction is such that it can create problem which we have to deal with it, and that is why it is important to understand the Peritectic phase diagrams very nicely. If you do not know the Peritectic phase diagram very nicely, you cannot control. To give you a hint, because those of you who are intelligent enough or able to understand my lectures nicely, you can actually bypass this Peritectic reaction. What is the meaning of bypass, which I will discuss detailed manner next class, but I am just giving you a hint. You can actually directly form beta from liquid instead of alpha. That means you can actually, you do not need alpha to form beta. Normal classical Peritectic reactions, you need alpha to form beta. Liquid is anyway present in the microstructure in the alloys. So you do not need alpha to form beta. So you can actually directly go from liquid to beta. If this is possible, if this I can do it by undercooling the alloy, what will happen? Because there is no gamma iron present, liquid directly NdFeB phase will form from the liquid. There is no soft phase at the center of this magnet, of the hard magnet, and we can produce harder magnet. This is a technology which has been mastered, which has been rather developed and mastered by the people in the world, especially in China, and that is why they could make very strong magnets, and those magnets actually are very useful and can be utilized for many applications. That is what is done normally in all the things. If you undercool the liquid strongly, you can get into this beta region. You can suppose undercool the liquid this much amount, from liquid to beta, this much amount I am talking about it. Then you can have a nucleation of beta is possible, and then beta can easily grow into the liquid and directly form it. You do not need alpha at all. That is exactly I am talking about to you, so that we can actually use this technique to control all the microstructures of peritectic reaction. So in the next class, I have introduced to you in this class the peritectic phase diagram, peritectic reaction. I have told you the problems of peritectic reaction, what are the issues we normally see. Next class I am going to talk about the different varieties of peritectic phase diagrams, okay, peritectic phase diagram followed by eutectic reaction, also I will talk about it, and I will show you some microstructures. By the way, I will start with microstructure in the next class, and then finally I will draw the free energy composition diagram for the peritectic reactions.